All right. So hello, everybody. So I'm going to discuss a tool for computing cosmological correlators that we find useful. So I want to present it, see what it's useful, and also what its limitations are. So that is the purpose of this talk. But before I do that, let me put this in a slightly bigger context, just to see why we're doing why we're doing all this. So I have drawn here the conformal diagram of a expanding universe, which starts possibly with an inflationary phase. That's what we believe is probably a good approximation to the early universe, which would be followed by some Friedmann-Robertson-Walker type, possibly decelerating universe. So after the inflation now, as you know well, the origin of the formation of structure in the universe is provided by the quantum fluctuations during the inflationary phase. So this is what I drew here. So if you want to compute some correlation functions at, say, towards the end of inflation, then when inflation is finished, you have nonlinear growth of these perturbations, which eventually lead to signatures that will be observable through either the cosmic microwave background or eventually also with a large-scale structure of matter in the universe. Now, we are not going to do any of this. We're really only going to focus on the calculation of these correlation functions. So we're not going to discuss the subsequent nonlinear evolution. It's a very interesting topic in itself, and there's much that can be said about it, but today we'll have nothing to say about it. Anyway, so that is the topic of this talk. And I should say that this has grown over many years now, maybe 7 years, out of a collaboration with many, many people, many smart people. I'd listed perhaps not all of them, but many of the people I've been working with recently are listed above. There's more to come. So this keeps going, gets more interesting. There's more people who are joining. So it's actually a very interesting enterprise and very lively and enjoyable, I should say. So I could encourage you to maybe join one day. So we'll see. Anyway, so the thing is now, as I said, we're not going to compute any of the nonlinear evolution. So we really focus on the quantum fluctuations in the early universe. Now, actually, we're going to make even more drastic approximation. We're going to assume that the universe was inflating eternally, never stopped inflating. So if you have it's like an eternal inflation, what that means is that the conformal diagram is not the future infinity, it's not light-like as it's indicated here, but it's actually space-like. So you have new future infinity. The conformal diagram would more look like something like this. So where this is a patch of the sitter space. So we are going to approximate, in fact, our space-time by an infinite inflation. So we call it just a part of the sitter space. And we're going to compute correlation functions at future infinity. So we haven't yet reached this future infinity, and we probably never will. So in a way, you might say that's useless to compute something that we will never be able to observe. But turns out it's still a good approximation. So if you take long enough wavelengths or distances, this can still be a good approximation to what happened, what is relevant for actually the present scale or the early universe. So, but just to make it clear, so the approximation which we're going to make is we assume that we have a de Sitter space, so a universe that's always inflating, and we're going to compute endpoint functions, cosmological endpoint functions in this background. And gravity is not dynamical, it's fixed. We just take a fixed de Sitter background. And what we're actually going to consider is we're going to consider a scalar field in this background. I'll say a little bit more about it later. I've also written down the metric for the de Sitter space here, at least for the Poincaré patch of the de Sitter space, which is conformally related to Minkowski space. So that is a valid criticism for much of which I'm going to say, is that the de Sitter space is almost or locally is in a way flat space, at least for certain type of field theories, and precisely the ones which are mostly the ones I'm going to be considering in this talk, but we'll come back to this in a little bit. So now there's two types of things that one can compute in the de Sitter space. So one is what people would call a wave function of the universe, or I should really say a wave function of some scalar field in this background. So in that case, you take some initial state. Let me take it to be the Bunch-Davies state. So that would be the initial state, which is basically an ingoing plane wave at my time minus infinity. So I've used conformal time here. And then you might want to start, this is my initial condition, you let this evolve. And then you may want to see what is the overlap with this wave function or with this state that evolves in time with a certain out state here. Let's call it out. So you would have something like Bunch-Davies. Then you evolve it with some unitary evolution, and you take the overlap with some out state. So that is what's usually called the wave function of the universe. Let's call this of out, something like this. So that is one thing one can compute. Another possibility, another thing that one can compute is what's called cosmological correlators. So in which case we are not going to put any boundary conditions at infinity, but instead we say we have an initial condition, we propagate this forward, then we do evaluate the correlation functions here and we propagate it back. So this is what's usually called the Schwinger-Keldysh formulation of a state that is completely determined by the in-boundary condition rather than the out-boundary condition. That's, of course, a much more physical thing to do because that is what one has control over. And this is the object which we're going to focus on. In fact, one observation, which I think is now becoming more and more accepted, is that cosmological correlators not only are perhaps more useful, but they're also simpler. In fact, in structure, they are simpler perhaps than wave functions. Why should this be so? Well, let us consider a typical or a special, not a typical, but rather a special model for our scalar field, which I've displayed here. So what we do is we take a scalar field which is conformally coupled to gravity. So that means, conformally coupled means, what does it mean? That it is invariant under conformal rescalings of the metric. So now you say, well, then now you're done. So in effect, you're just doing Minkowski space, right? So because the sitter is already conformally related to Minkowski space. If you then furthermore take a field theory, which is itself conformally invariant under rescalings of the metric, and say, well, you're just doing a calculation effectively in Minkowski space. This is true to a large extent, but not completely. For two reasons. One reason is that the asymptotic boundary of the sitter space is not a null infinity like you would have for Minkowski space. For Minkowski, the asymptotic future infinity would be like this. While for the sitter space, the future infinity is space-like. So it's a different space. Locally, of course, it's the same, but asymptotically, they're not the same spaces. So that should somehow reflect in the correlation function. Another thing which will play an important role is that the isometries of the sitter space are not the same as in Minkowski space. And as a result, one will have to be a little bit careful when you say you have to deal with ultraviolet regularization, for instance. Okay, so now the thing is set up. Now I'm going to take an illustration. So we're going to take this model for now, which is just a conformally coupled scalar field in the sitter space, and let us do a calculation. Say, let us suppose you want to compute the 4-point function at one loop. And this talk is mostly going to be about loop corrections to cosmological correlate. As I said, I take, let me first start, in fact, in flat space as a review, let me take a massless field, lambda phi 4, in Minkowski space. That calculation can be done. It's given, and we know what, in fact, the result is. It's just pull this up. So it's this loop diagram, right? You have a loop like here. So you have maybe a Q propagating here, and then Q plus K. K is the external momentum that flows into the diagram. So you do this calculation is UV divergent. So let's put maybe a cutoff here for now, just UV cutoff, and then the result is going to be K squared over lambda squared, where K is the external form momentum. So in flat space, this calculation is, of course, standard textbook material. So now, how would that be look in the sitter space? So in the sitter space, again, we take a conformally coupled field, but we do the Schwinger-Keldysh contours, which means we have, first of all, two things that have changed. We have time dependence of the vertices. So we don't have time independent background, right? So we don't have time translation invariance, so that we will still have to integrate over the time, so denoted by eta 1 and eta 2. And we have time-ordered and anti-time-ordered propagators. That's a peculiarity of Schwinger-Keldysh formulation that I will perhaps not review here. But let me just write down the green function, say the propagator that will enter. It will look something like this. So for a conformally coupled scalar field, it's rather simple. It's a Hankel function where q is the momentum, the spatial momentum, eta1, eta2 are the times, and there's a product of Hankel functions. Now, one thing that we're going to do is we're going to Wick rotate. Now, the thing is, if you Wick rotate time-ordered propagators, you Wick rotate them upwards. Like you go into the upper half plane. Anti-time ordered propagators, you Wick rotate downwards, so you go down. So then I put here little arcs. This is not relevant for discussion today, but will be relevant if you have IR divergences, which is not uncommon, as you know. Then that's a whole different topic, which I will not talk about here today. So suppose we've done this thing. So we do Wick rotate these correlation functions. Then what happens is you rotate into Bessel functions, and what will happen here is I've done two things. First, I've Wick rotated, but I've done one more thing here to go to this equation. I also used something like a spectral representation of sorts. It's called spectral representation. That is, I introduced some sort of dummy variable, omega, over which I integrate, and then the omega integral just replaces this omega by q, so which is this q up here. So it's just, somehow I wanted to look a little bit more like flat space one propagator. And this looks already very much like a flat space propagator. Of course, we still have these functions, sine of omega eta and here and cosine. Which ones you take depends on the boundary conditions. Has to do with this retarded and advanced correlation. So now that's the first step. So now we've just not done too much. We've just rewritten these propagators. As I said, the purpose of this whole exercise is to rewrite these Schwinger-Keldysh amplitudes or correlators, rather, in the Sitter space into something that looks more like a flat space amplitude. And that is what we want to achieve. Okay, so we've done this thing. Now, the next thing is we should now insert this into this diagram. We have just a propagator. We should insert it into the diagram and then do the integral. So let me give the result. So I've just rewritten these propagators in the Fourier representation. And remember, I had this cosine and sines. It turns out that if you take the sum of time-ordered and anti-time ordered, only a cosine will survive. Then these are the loop integrals, which are already very familiar to the flat space loop integral. Let me go back here once more. This is very similar to this form. Then we still have these cosines, so that is precisely reflecting the fact that we don't have a null infinity, we have the space-like infinity. And then we have these bulk to boundary propagators, which I perhaps have drawn here or before. They are reflected by these structures here. K12 is the ingoing energy, and then Z1 and Z2 are the two variables which I have obtained by Wick rotating eta2 and eta1. So I still have to integrate over Z1, Z2. I'm going to integrate over Z1 and Z2 now. Let's do it. What happens is if I integrate over Z1 and Z2, that together with this term is something simple. It's just going to give you an omega squared plus K12 squared. This I remove. I get a omega squared plus K34 squared. So this is the outgoing energy. And this is now gone. I've done the Z integrals. So now you see, what have we achieved? So we've achieved something that looks like the flat space one loop integral, but it's not quite a flat space because you still integrate. You see, this is part of the external energy for the flat space integral, but we integrate over this energy. And this is just the result of the fact that we don't have time translation invariance in the Sitter space. So we have to integrate over the energy. It's a bit like in celestial amplitudes, you also integrate. We don't integrate over the spatial momentum. That's just fixed because we have translation invariance, but we have to integrate over the energy. So if we go back here, we have to integrate over the energy that's contained in that loop. And it's weighted by this function. And this is the energy, and it's weighted by this function. So it's just a weighted energy integral. Great. So now let's do a diagrammatic representation of this. I've written it down here. So here's our flat space integral. And then these weights here, I just wrote them as dashed lines. And I just wrote this here. And you see, what we're going to do is we're going to pretend these are propagators. Now, I say, of course, you can call whatever you want to call, but it's still just weight functions. Is correct? They're just weight functions. It's just one-dimensional integrals with some weight function. But I'd like to think of them as propagators. I can put I epsilon prescriptions and so on. That's all working fine. Suppose I do that. Then we get this type of diagrams. Now I say, okay, looks a little bit like a flat space diagram, but now one higher loop. So it looks like a two-loop diagram. And well, okay, it's what it is. We have to live with it. But this is the kind of structure we get. And we want to argue that this is true for a rather, not for every diagram, but is true for a rather big class of Schwinger-Keldysh correlators, can be written as flat space diagrams, which are dressed with some extra propagators, or if you want to call them weight functions, but we like to think of them as propagators. That structure, as I said, is not generic, but is still fairly universal. And what is also true, though, is that the nature of these extra, what we call propagators, will depend on what kind of interactions you have. Say, if you have a phi cubed interaction, will look a little bit different. You still have this, so you have here we have a three-level exchange diagram with these dash propagators, but now they involve some extra S integrals, like a two-dimensional structure. So the nature of these extra propagators depends a little bit on what theory you have. But you see now the three-level exchange in the Sitter space looks like a one-loop triangle integral in flat space. Looks like it's not quite the same, but it turns out that the transcendentality of the function is the same. So there's a lot of similarities now that we see appearing, and you can see them at the level of the integrals even. Okay, so that is the first thing I wanted to say. The second thing I wanted to say is this diagram, which we started with, is UV divergent, right? Because this D4Q integral is logarithmically divergent, so you have to regulate it. In the flat space, we just put a cutoff, is one way of doing it. Or alternatively, you could say, let's not put a cutoff, but let's do like 4 minus 2 epsilon. Let's do dimensional regularization. Fine. That's all good. The only thing is these regulators do not, while they preserve Poincare invariance, so in that sense they're good regulators, they do not preserve the de Sitter invariance. So if whenever you compute something with such a regulator, the result would be given by this, it's not going to be de Sitter invariant. You do not satisfy the word identity. So what you're going to do is you have to think of another regulator which preserves the symmetry. And one way of doing that, I wanted to put it here, is that you could simply change the power. Let me put here a 1 plus 2 kappa in the propagator. I change the power of this propagator. That is pretty much equivalent to dimensional regularization, but it does break de Sitter symmetry. But if you put here a 1 minus 2 kappa for the Z dependence, then it no longer breaks the Sitter invariance. So that is what we call the analytic regularization. Suppose one does that, what happens is that gets modified. This thing gets replaced by something like K12 plus K34. So squared. So now we see, now this thing is manifestly de Sitter invariant. In fact, just the demanding that is de Sitter invariant would give you these two structures, but it wouldn't fix like the coefficients in front of it. This calculation is a prescription, but one can argue, in fact, using integration by parts identities, which we can again use, just like in flat space, you can actually fix these guys. And so you can determine the result uniquely. So in these dressing rules, in these dress propagators, you can use these tricks. I'll come to that again in a moment. Okay, so I'm running out of time. Let me just come to the discussion. So what we've argued is that the dressing rules, thinking of this dress, taking flat space amplitudes, dress them by these dash propagators, in a way, it's just a systematic rewriting of some cosmological correlators, but they do have the advantage that they make manifest the relation to flat space Feynman amplitudes. And once you have made this relation manifest, you can do things which we do like to do in flat space. Like you can take 4-point function, you can cut it. And we know how to do that now in the Sitter space as well. We can take unitarity cuts, we can do dispersive integrals. I think Chandra in his talk will perhaps say more about this, so I would like to refer about that.